In this video, let us understand singularity of complex valued function. First, we need to know what does regular point means. Suppose f is complex valued function defined in some domain D and z0 is an interior point in D. When we say that f is regular on z0 or z0 is regular point of f if there exists delta greater than 0 such that derivative of the function exists for all z belonging to delta neighborhood of z0, that is modulus of z minus z0 is less than delta. Let us see this through example. You are given a function fz is equal to 1 upon z, and we all know that this function is differentiable at all points except 0, because at z is equal to 0 f of z is not defined. Hence, set of complex number complemented singleton 0 is set of regular points for this function. Similarly, known functions like f1z equal to modulus of z, f2 of z is equal to real part of z, f3 of z equal to imaginary part of z. Do they have regular points? And if yes, what are the regular points? Let us consider first function, that is modulus of z. This function is already known to be nowhere differentiable. And why not? Because Cauchy-Riemann conditions for differentiability for any z belonging to C is not getting satisfied. So f1 of z equal to mod of z does not have regular points. But f2 and f3 satisfies CR conditions only for z is equal to 0. Hence, all the above functions given, that is modulus of function, modulus of complex number z, real part of complex number z or imaginary part of complex number z are nowhere regular. Okay, that means I should have some criteria to say that whether the point will turn out to be regular or not. Let us have this theorem. It says that if f is regular at z0, then there exists an open disk around z0 such that every point of this disk is regular point. So what we are given? This z0 is the regular point of function f, or I can say f is regular at z0. Then by definition of regularity, what we have? Derivative of function will exist for all z belonging to this delta neighborhood of z0, that is mod of z minus z0 less than delta. Now let one more point, say z1. Okay, let z1 belongs to this disk. So what you have? Modulus of z0 minus z1 is less than delta 1, and let us define delta 2 to be delta minus delta 1. So we have two deltas, delta 1 and delta 2, and from that we choose this delta dash to be minimum of delta 1 and delta 2. So in that case, what will happen? if I take z1 as the center, then modulus of z minus z1 will be less than delta dash, because it will satisfy the condition of delta 1. And obviously it is subset of the whole disk. So subset of modulus of z minus z0 less than delta. So our definition of regular point says that z1 is regular point. So in general, we will have all z belonging to this disk. Mod z minus z0 less than delta are regular points. So what I can have, that does not exist isolated regular point. That is what conclusion from this result. Okay, now we are in a position to define analytic function. A function f of complex variable z, so you can say complex valued function f, is analytic in an open set, say S, if it has a derivative everywhere in that set. Okay, that means it is analytic at a point z0 if it is analytic in some neighborhood of z0. So first statement is definition or criteria when a complex valued function is said to be analytic, and second is in fact a characteristic, that is a complex valued function is analytic at a point z0 if it is analytic in some neighborhood of z0. So we have some observations. Function f is said to be analytic in S if it is regular at every point of S. When function f is analytic at a point z0, it must be analytic in some neighborhood of z0. And third observation is, if a function f is analytic on the set S, then the set S is open. Hence, if we should speak of a function that is analytic in a set S, then it is not open. It is to be understood that f is analytic in an open set containing S. Okay, and this conclusion is from above three observations from the theorem. Once I know analytic function, I can define entire function. Entire function is a function that is analytic at each point in the entire plane. That means if a function turns out to be analytic in the whole plane, then we call complex valued function to be entire function. Best examples of entire functions are f1 of z is equal to z. You can differentiate infinitely many times and it exists, all the derivatives. Similarly, exponential function is also entire function. Polynomial function and sine function are entire functions. One can also check that f5, if I say f5 of z equal to cos of z, is also entire function. So these are entire functions because they are analytic at each point in the entire plane. Okay, then let us have some example where function turns out to be analytic. First one is example 3 is find a set in which the function f of z equal to 1 upon z is analytic. So I need to know where this function is differentiable. Okay, and one know that the derivative of f of z say f dash z equal to minus 1 upon z square exists at each non-zero point. So what this says, the function f is analytic on set of complex numbers complemented 0. That means except at 0, function f of z is equal to 1 upon z is analytic. One more example. Find a set in which the function f of z equal to modulus of z square is analytic. Now here f of z equal to mod of z square, and z is x plus iota y. So mod of z square is x square plus y square. This function is differentiable only at z is equal to 0. So we can say that it is not analytic anywhere. Okay. Now if function fails to be analytic, then what should be the characteristic of that point? So we are in a position to define singularity. If a function f fails to be analytic at a point z0, but it is analytic at some point in every neighborhood of z0, then z0 is called a singular point or singularity of function f. So it should be quite clear that complex valued function is not analytic at that particular point, but it is analytic in some neighborhood of z0. Then the point is called singular point or singularity of f. The limit point of the set of regular point is defined as singular point if it is not regular itself. In one of the video we had defined limit point. Okay. In previous slide we had proved that z is equal to 0 is singular point for the function f of z equal to 1 upon z. But f of z is equal to modulus of z does not have any singular points since it is nowhere analytic. Okay, then I am in a position to define what does isolated singular point means. A singular point z0 is said to be isolated if there is a deleted epsilon neighborhood, say 0 less than modulus of z minus z0 less than epsilon of z0 throughout which f is analytic. That is, in the deleted neighborhood, say epsilon deleted neighborhood of z0, if function remains analytic, then the point, that is singular point z0, is said to be isolated singular point. For example, the point z equal to 0 is singular point for the function f of z is equal to 1 upon z. Now let us take any deleted epsilon neighborhood of point z is equal to 0. Then we know the function f is analytic in entire neighborhood. So the singular point f of z is equal to 1 upon z is now labeled as isolated singular point of the function f of z equal to 1 upon z. Consider this function f of z is equal to z minus 1 upon z square into z square plus 9. Now let us find what are the singular points. So what I need to do, you equate denominator equal to 0 and find the roots. So here once I put denominator, that is z square into z square plus 9 equal to 0, then I will get 4 roots. For z square equal to 0, we will have 0, 0. And for z square plus 9, we will have 3 iota and minus 3 iota. So repetition is not allowed. So what we can say, the function, that is z minus 1 upon z square into z square plus 9 has 3 singular points, 0, 3 iota and minus 3 iota. And all these 3 points are isolated singular points. That means if I remove this point, then function will remain analytic in the given neighborhood. Now non-isolated singular points. Quite obvious. The limit point of a singular point is defined as non-isolated singular points. Let us have example. Find non-isolated singular points of function tangent of z. Now tangent of z is nothing but sine of z upon cos of z. And to find singular point, I need to put cos of z equal to 0. Okay, and you know that cos z is equal to 0 means z is equal to, that is multiple of pi by 2. So 2n plus 1 pi by 2, where n is an integer. So we have z is equal to 2n plus 1 pi by 2 to be singular points of the function. Here, the set of singular points does not have any limit point. So all the singular points are isolated singular points. So we have one conclusion, that is the function does not have non-isolated singular points. One more example. Find isolated and non-isolated singular point of function f of z is equal to tan of 1 by z. Now tan of 1 by z is sine of 1 by z upon cos of 1 by z. So what are the regular points? Sorry, what are the singular points? It is 2 upon 2n plus 1 pi union singleton 0. N is integer. Now note that the limit point of the singular points is 0. So we have only 0 as the non-isolated singular point. And other singular points, that is 2 upon 2n plus 1 into pi for any integer n, will be isolated singular points for the function tan of 1 by z. One more example, I am leaving it for you to check. Note that hint is already given. We have a function f of z is equal to 1 upon sine of pi by z. We want to find what are the isolated and non-isolated singular points of this function. For singular points, our criteria is denominator should be equal to 0. So sine of pi by z is equal to 0. That means it is 1 upon n for n belonging to any integer except 0. Union 0. Now why we are removing 0? Because otherwise this function will not be defined. So isolated singular points are 1 upon n for all n belonging to integers except 0. And non-isolated singular points are only singleton 0. So note that if the function f has finite number of singular points, then all those points are isolated singular points. Thank you.